All right, it's 4 o'clock, so I think we should get started. So welcome everyone to lecture 26 of this class. So there's only 28 in the semester, so this is how far we have gotten. And today we will be talking about rotation and 3D representation. So you can see what this robot is looking at. It's like a 3D thing, and it also has some rotation to it. So I'm very much looking forward to today. So some logistics. So we are actively working, or well, the TAs are actively working on grading homework 3 and lab 3. Lab 4 and homework 4 will be due April 26th. So that's the end of next week. So just keep that in mind. If you have late days, you can go beyond that, of course. And then final exam, May 1st from 4:30 to 6:30. I don't actually know where the room is. I have to double check where it is. So I'll try to make sure everyone's aware of that. So, and then yeah, use 2 cheat sheets. I mean, you can use 0 or 1 if you want an optional challenge, but most of you will use 2. And then yeah, otherwise there's gonna be similar policies as the midterm. So like if you need some kind of academic accommodation, just make sure you clear that up with me before. All right, question. I have my iPad open, so you can type in some stuff, but that's also because I have some notes on some of the math, so I'll be switching back and forth. So I may be a little bit delayed if you're typing in some notes here. All right, so just a quick recap of what we talked about earlier, then we'll continue with the main topic today. So if you remember last time, we talked a lot about simulators and roughly how they work, the equation of the motion of a Lagrangian, and then methods that you have to do to discretize them to actually get them implemented on a computer. Now, once you have the simulator, how do you use it? Well, if you're using a machine learning approach, that means you need a lot of data. And sim to real and specifically the domain randomization is a specific technique and a very popular one for randomizing many properties that you see in simulation, especially the visual one and the physics properties. So that like if you're trying to train from an image where the robot should grasp, like how it should do like grasping or manipulation, maybe we just randomize all the vision parameters, all the camera angles, all the like other things like brightness, and then the real world is going to be inside the distribution of your training data if you make it broad enough. So yeah, sim to real and domain randomization has been a very effective technique. And we also talked about this paper. So this one was about using a simulator to train a robot hand that could rotate object with tactile information. So this is the simulator. And these are the physical results. And then the tactile sensors that they use. So again, just one example, which I hope makes you interested in potentially using robot simulator for your own work. And it's also helpful for faculty because I don't want students using my physical robots until they've shown that something works in simulation. And then I trust their result more so that they can use our physical robot. So. All right, so moving on to the main topic for today. We are talking about rotation and 3D concepts in robotics. So the only related thing that we covered here was like rotation matrices from earlier, but here we're going to cover rotation in more detail, especially talking about some of the other representations that are commonly used. And then we will also talk about 3D representation because robots operate in 3D, so many times if we have some robot and we're trying to program it to do something, we might want 3D data instead of 2D data, because the robot has to reason about, what is the 3D geometry of a scene, to be able to properly grasp and do other manipulation and related tasks. So what I find really interesting is that both of these topics, they're both fundamental. So in some sense, I feel like I have to cover this because I don't want you to take an intro to robotics course without covering these concepts. Because if I told my colleague, we never talked about quaternions in detail, they would tell me, why didn't you do that? But the other nice thing is that they're also very relevant from a research view. So people are still doing a lot of research that is very related to this. So for example, I'm organizing this very awesome workshop in a few weeks in one of the biggest robotics conferences. So the 3D visual representation for robot manipulation. So we have a lot of great submissions there. So check the website if you want some cutting edge research in this area. I mean, obviously, since I helped to organize it, I think it's good, but I can point you to some other stuff if you want other, less biased sources. So, hi, yeah. So any quick questions about why we're studying this? All right, so we'll talk first about rotation, then we'll talk about 3D representation. All right. So remember that we were talking about orientation. And then we talked about rotation matrices. So an example notation, which one of the textbooks that we have for the course uses is as follows. So there are 9 numbers in a rotation matrix, but there's only 3 degrees of freedom because there's like 3 axes where you can rotate objects. So there's 3 numbers. 3 numbers is the minimum that you need to specify, which we covered that in one of the earlier courses, earlier lectures. Now, the independent constraints are the column being unit vector. So again, if you see that, the symbol is the same as the Euclidean norm. If we don't put a 2 down there, that's the default. I mean, sometimes we put the 2 there, sometimes we don't, but then there are constraints on the column being orthogonal. So you have 2 vectors, you take their dot product, it turns to 0. Geometrically, that means they're perpendicular to each other. So think of like the x-axis vector and the y-axis vector. They're perpendicular. So yeah. And then I explained earlier that my intuition about what is an independent constraint is that you can change it from satisfied to unsatisfied without affecting all the other constraints. Or you can change it from unsatisfied to satisfied. So we also talked about some common rotation matrices. So this is notation used from one of the other textbooks, the modern robotics one, which I'll be using mostly for the next few slides. And when we're talking about rotation matrices, the easiest thing to do is think about a rotation about one axis instead of like all 3 of them together. So just think of a rotation about the x-axis or the y-axis or the z-axis first. Just one rotation about that, and then worry about combining them later. So everyone remember what the rotation matrices look like? Like rotations about the z-axis by angle alpha. If you don't remember, put it on your cheat sheet. So one way to remember, the one way that I remember is that it's like a 2D rotation. You have your cosine, sine, cosine, where the negative is by one of the signs. And then the rest of it is, you form the 3rd row and column, and then there's a 1 where they intersect and a 0 where they don't. So yeah. So these are like rotation matrices that you can use to represent a single rotation about the map. Yeah. And remember the right-hand rule as well. So you have your thumb, and then it points in the direction of the axis, and then positive means you curl in the direction of the finger. So Yeah, that's the convention the community follows almost always. So just make sure that we are following it as well. Right. And we also talked about how to combine the orientation and position. So, the set of rotation is this group, so the special orthogonal group of 3x3 matrices, which are rotation matrices. So like that means if you take their matrix, you transpose it, then you multiply it by itself, you get the identity matrix. And if you want to include a position component, then you can form a 4x4 matrix that combines the rotation and the position together. And then the zero here is like 3, 0. So 0, 0, 0, and then a 1. Yeah. All right. Now one more thing until we get to some of the new stuff. So remember that we talked about different rotation matrices and rotation representation. And the advantage of rotation matrices is that we can use linear algebra to do rotation, which is very convenient. So it's easy to do like composition, like you can multiply rotation together by doing matrix multiplication. But the downside is that, well, yeah, maybe you have to have more numbers in the representation. So it's a little bit inefficient in that sense. But sometimes that's the trade-off that we get. As you'll see today, when you have more explicit representation that use fewer degrees of freedom, they get singularity. So, and we talked about the fact that there's Euler angle, axis angle, quaternion, and then some other more advanced rotation matrices. Yeah. And again, these are equivalent, like so they represent the same thing. So you can go from one to the other. And if you're using code, so for example, you might use something like PyTorch 3D, which is an example code that I used before to go from, an axis angle representation to a matrix representation, or a matrix to quaternion. And again, this is just one example of some code. I'm sure there must be others that help do the automatic transformation for you. In fact, it's generally a good idea to let code do it for you, because because of like singularity and other things, it's a little bit tricky to make sure you cover all the edge cases in the rotation representation transformation. All right. All right, so let's start off by talking about Euler angle. But before we even do that, we can't just say Euler angle. We have to say something Euler angle, right? So I wrote that here. We have to say ZYX Euler angle. So the fact that I wrote ZYX, what did that suggest? Can you do like XXX Euler angle? I mean, I wrote something here, right? Yeah. Is it the same if you rotate about the z-axis and then the y-axis and then the x-axis? Is that the same? If the angles are the same, is that equivalent to doing them in the reverse direction, like x, y, z? Yeah. Think about that. It's yeah. So the ordering matters. So you have to make sure that you apply it in the right order. So when we're talking about the ZYX Euler angle, we're going to consider there is some rigid body with a body frame. So if you want to use the example that the modern robotics textbook uses, the B would be like right at this corner. Yeah, so that's like the body frame. And then the ZYX would mean you make 3 successive rotations with respect to that. So you rotate about the z-axis first, then the y-axis, then the x-axis. It's got to be in that order, otherwise you're doing something different. Yeah. And then you combine these, so you have a bunch of these matrices that you multiply together, and that is one rotation matrix that covers all three of them. So you get the equivalent thing if you just apply this matrix. Yeah. And you'll notice that there's three numbers here. So the Euler angles are a 3 degrees of freedom representation of rotation. Yeah, so because we need three numbers, and then we can just put it in, we can just form the rotation from that. So any questions about this setup? Yeah, what?
Which direction? Right corner to the left corner, the whole direction of rotation to this both will be different.
I think what you're asking is, how do we decide where the body frame is? That's something we have to decide. Yeah. I mean, usually the body frame is something that is like what we would intuitively think about the origin of something. So for a robot manipulator, often the body frame is like the base of the robot, like where it meets the table. But in general, you can pick where the body frame is. And yeah, it depends on where the body frame is. Like if we change the body frame, the book will rotate in a different way. Like that's just how rotation works. So that's why we have to specify a body frame first. Yeah, yeah.
Is that the identity matrix over there? Oh.
Yeah. So I think the appendix of the textbook, yeah, I think they meant to put an I there. I don't know why, because you don't actually need it. Yeah. I mean, you don't need the identity matrix there. Fine. So if you were to multiply, so if you took all the three matrices, you multiply them together, you get something that looks like this. So hopefully it's all familiar to you, like because of all the C's and the S's that we've written, like those represent the sine and the cosine of like alpha and beta and gamma. So that is mostly, it's like our dynamics lecture, mostly straightforward matrix multiplication. So you can do this on your own to verify. I won't do it here. So this is like, how we would just write out this 3-parameter rotation in just a matrix form as a function of the three Euler angles. And here's, all right, so here's one way you can try to visualize what the Euler angles mean. So this is in the appendix B of the modern robotics textbook, but I'm just gonna explain a little more about what the figures. So they're using the wrist mechanism to visualize Euler angles because sometimes that's a little bit easier than just like a single object because you have like 3 different ways that something can rotate. And what you see here is that this is supposed to represent where all the angles are set at 0. So this is like the home position or the origin or the origin of some system. Now, there's going to be 4 reference frames. One reference frame is over here, so that's 0. So if you remember the modern robotics, they put the bracket and then there's something inside that represents some frame. So there's frame 1, well, frame 0, frame 1, frame 2, and then frame 3 here. Yeah, hopefully it's a little bit clear to see. If not, this is straight from the modern robotics appendix B. So, and what you see here that, all right, suppose that this whole mechanism rotates by gamma, and that's it. So what changes here? So if the gamma is the only thing that is non-zero, then it's gonna rotate about this axis, which is only gonna change 3 here. It's not gonna affect 2, 1, or 0. So that's the way to think about it. They didn't really, like, the textbook didn't really clarify that, but like that's basically what they mean here. So when you're rotating by gamma, you're only changing 3 here. You're not touching the other. But when you're rotating by beta, that's gonna change where 2 is located. Like that's gonna move it somewhere, which is also gonna change where 3 is gonna move. But it doesn't affect 1. Yeah. And then if you rotate about by alpha, which is over here, the whole thing will move. Is that clear? Yeah. What?
Can you explain why rotating, rotating by beta does not, changes 3? Yeah.
Yeah, so why, if you rotate by beta, it's gonna change 3.
Yeah.
Well, so I don't think it's gonna change the position, but it might change the orientation of, like, that frame might rotate. So you have like, I don't have a mechanism, but if you think of it like this rotates like well, this will go down here, like over there. This goes down here, this thing will just like go on.
Is there just right off the bat, is there a general way that we can apply to kind of figure out what changes, what doesn't, or does it have to, do we just have to visualize it in our heads?
So in general, how do you know which rotation affects which part of this? Yeah, I'm not sure if there's a good answer to that. I think in my opinion, what if there's a diagram that I see that like this, it should explain in the caption or the text, like which, if you rotate by this angle, which parts actually change. So I only know this because that's what makes sense to me when I read the book and then I see this diagram. If it comes to like, if I'm going to ask you this, I'll tell you which rotation affects which parts of the structure. Yeah, it's
Just to be clear, the rotation by beta, that changes the orientation of the third body frame, so body frame 3, but it only changes the position of the second body frame, not the orientation, correct?
yeah, it should. Yeah, rotating by beta should change the position of where 2 is. Like 2 is like if here's an example. This is what happened when you rotate beta by 90 degrees. Like this, so this thing which had 1, it stayed the same. But this thing rotated like by 90 degrees from here to yeah. So yeah.
I'm just curious about why the framework 3 will change if we rotate the X step from the left here, right here. But I thought the whole framework will be stuck, right? But it speaks on the top, if you rotate it at the bottom right here, the whole framework will stop.
So you're saying something will be stuck
Yeah.
here? How? Wait.
Um,
So I think I was saying let's not think. I think this is mainly a way to try to visualize Euler angles. Like it's one way to do this. Like it's not the only way. Mainly I'm putting it here because it was in the the appendix of the textbook, and I wanted to clarify what they were trying to show here. I don't think anything will get stuck here. Like I think you can think of this being able to allow any rotation from like 0 to 2 pi for any of the angles. Like if you rotate, if you rotate by alpha, you can move in the entire interval 0 to 2 pi. Like any of those rotations is valid. The same thing for beta. You can rotate it from 0 to 2 pi. That's the entire range of rotation you can get. It'll just rotate like this length will just rotate, continuously if you just rotate by beta.
If we rotate the gamma right now, just like at the left figure right here, the whole framework will be stopped, right? If we just make a 90-degree rotation.
I think maybe what you're asking is going to be more clear when we talk about gimbal lock, which happened. But the confusing thing is gimbal lock is such a misleading term because nothing is locked. I mean, you can still move the structure. It just gimbal lock is it's mainly meant to specify that you lose a parameter when you describe, the rotation. So maybe let's see. I took a GIF from Wikipedia about the gimbal lock, which kind of looks like this. And I linked a few videos if you want to look into what it means a little more. But yeah, if you rotate by 90 degrees, you do get this, and then essentially what it means is the rotation about gamma and then alpha, you get the same set of rotations. So it's not stuck. It just means you lose the ability to express a different type of rotation or orientation of the whole system. Yeah. So, but yeah, these are some good questions. Yeah. So okay, let me move this. Yeah. So in order for us to say that the Euler angles are a valid rotation representation, what we have to say is this. Given an arbitrary rotation matrix, there exists some values of alpha, beta, and gamma that satisfy the above equation or the above matrix. Does that claim make sense? Because like any rotation matrix, we've got to be able to express it using the Euler angle. Otherwise, it's not a rotation representation. So, yeah, and then if this claim is true, then that means the ZYX, I keep messing around the order, but the ZYX Euler angle can represent all possible orientation. Yeah, those are some pretty important claims. So let's talk a little bit. Let's talk a little bit about this thing here. So I remember there was one class when we talked about the two argument arctan function. So you have a tan 2, right? So a tan 2 is a function that tells you for some values of y and x, what is the angle theta formed from the ray that extends from the origin to xy. And theta is confined to negative pi and pi. Yeah, so that's what the a tan 2 means. And also just remember that the really annoying thing is that the y comes before x in the argument. So yeah. All right. So in order for us to show that ZYX Euler angle can represent all possible orientations, then we've got to show that suppose we have some rotation matrix, what are the beta, alpha, and gamma values? Like that's what we've got to show. So let me do some of the computation here. All right. So Alright. So we have some arbitrary rotation matrix. We gotta show that you can satisfy that equation, right? So the way to do this is to start setting some of these values equal to their counterparts here in the R of alpha, beta, and gamma. And then once you do that, you solve for the three angles. So alright. What is R11 squared plus R21 squared? So if you look at that, we get, so those are over here. So we get cosine of alpha, cosine of beta. C alpha. Plus. Yeah, sorry, if you, yeah. So what happens here?
Cosine beta squared, because cosine alpha squared plus cosine alpha squared is one.
Yeah. So, all right, this thing goes away, then you get C beta. All right, so we have that. So it already seemed like we can try to solve for beta. And you can kind of see that, you can kind of see where this is in, because like you have R11 squared plus R21 squared already in there. So. Oops. Let's go over here. Let's go over here. Actually, let me one more thing. So. ah, So this is just, we take the square root and then we get cosine of beta is equal to plus or minus this, this term here. So the next thing we'll do is we want to get something like that. And if you look at negative R31, that's over here, right? So that would be positive sine of beta. Yeah. Yeah. And then so do you see how these solutions follow from the math that we just did? So if we have this A and remember that the y comes before x when you write this. This is a super annoying thing, but all right. Then if so, so what this is really referring to is really referring to like it gives you the arctan function, but handles the proper like sign in the quadrant for you. So now, for example, if this x is greater than 0, like if you're over here, if you're in this shaded region, then this thing is basically arctan of y over x. Like if you look at the formula for how this is derived, you basically get from. Now, what we have is x here is like our thing over here, so this thing is positive because the we took the square root of the positive number that we're assuming is a positive. And then you get, minus R31 over there. And so if you plug it in over here, you get and we remember that, we can plug in what the R31 means, right? And then this would be sine of beta. Super. Oh, so. So I think the better way to write this is you would first make this equal to minus R31 over square root of R1 squared plus R2 squared. Like you get this, and then what this is basically giving you is like what the beta value is. So you get like your beta value here, and then from this you try to solve for the alpha and the gamma. So I think that's the way that you would try to do this algebraically. And if you try to do something like if you go from here and you try to find the values of alpha and gamma, you end up getting the relations of let me get that from here. So this thing would turn into, so we have 2, 1, which is two, actually, so if you look at what the values mean here, like you get R11 that goes over here, and then the same thing for R21. And when you do this, you can remember like what the definition of the tangent is. So you have the tangent of alpha is equal to the sine of alpha divided by the cosine of alpha. And when you get this, if you frame it into this formula, then you divide through by the common term, and then you get like this relation. And then you apply the arctan function, and then that's how you get your output. So. And this is also why we have to put a condition that the cosine of beta is non-zero, because otherwise that's why we have the not plus or minus 90 degrees, because if you do cosine of 90 degrees, you get 0. And the cosine of 90 degrees, that's the gimbal lock thing that I kind of mentioned earlier. So. Yeah, so hopefully this was, so it's a little bit. I think it's conceptually, a bunch of elementary trigonometry to find your beta, alpha, and gamma, just some tedious computation to get there. So what I hope is that this just gives you an initial beginning. If you had to like prove like that there exists any beta, alpha, and gamma value that make it equivalent to some arbitrary rotation feature. Like these are like the rough steps that. All right. Yeah. Oh yeah, yeah. Well,
Oh, you don't actually need beta for the alpha calculation, right? Is it just, you just divide through it basically?
we you don't need the beta. You just need to make sure it doesn't lead to cosine beta equals 0. That's the main thing that you need. That's why you need this thing here. Yeah. Otherwise, you get a gimbal lock. Yeah. And then so if you have this, then you get a one parameter solution. But what that basically means is you lose a degree of freedom that you can use to describe your rotation. Yeah. So again, what I hope this is like the way that I think of that my thought process of how to interpret this claim. So. All right. So when we talk about the ordering, the ordering matters when you use Euler angle. So you have to do something like if you're using VYX, you've got to do a rotation about the Z axis, then the Y, then the X, right? Like you can't do it in different you can do it in different orders, but then you get a different type of Euler angle. So there's a lot of them. So when you're coding this up, just look at your documentation and make sure you're following the right ordering. So that thing is a little bit annoying, but it's not like a deal breaker. I would say that for many people, the deal breaker for Euler angles is gimbal lock. Yeah. So gimbal lock means the example is when you have the beta is plus or minus 90, and sometimes you'll see that being called like the pitch has plus or minus 90 degrees, but I don't like using those terms because I never remember which one corresponds to which X, Y, Z, and I prefer to just use Z, Y, X or like make the axes explicit. Like that's my personal preference. Now for gimbal lock, the name is awful. Okay, it's not locking. It's not nothing. The gimbal mechanism that you see there, it's not like it's not locked. It just means you can't like command all types of rotation. So you should think of it as the outermost. I think for this one, it's like the outermost and then the innermost gimbal mechanism. If you rotate them, you get the same effect. Like so you have two different gimbal mechanisms, but if you rotate one of them and then you rotate the other one, like they have the same effect of like turning this aircraft like vertically just around the vertical axis. So the whole point of the gimbal mechanism there is that we have 3 different mechanisms and 3 different ways we can rotate the object. Yeah, so if you look at some of the like this video has a pretty good example, and it shows like how gimbal lock was popularized by like spacecraft mission, because the people who had to command spacecraft or spaceship had to make sure that they avoided gimbal lock. But the right way to avoid gimbal lock is to use something other than Euler angle. But if you're only dealing with 1 or 2 degrees of freedom of rotation, which is very common in robotics. So in robotics, we might have a tabletop than the robot is just grasping something. And there might be only one orientation, maybe it's just an orientation about the vertical axis so that a parallel jaw can grasp like this or like that. But there's only going to be one rotation axis. So in that case, Euler angles are fine. Like they're probably easier to understand anyway. But if you say you rotate by 90 degrees, you probably think of an axis and then something changes by 90 degrees. So yeah, but it's for this reason that like some books don't even like refuse to cover Euler angles as a rotation representation. I mean, I think it's important to cover this to understand why there are alternative rotation representations. So yeah, some more resources there if you want to take a look at them. Yeah.
Can you give us a little bit of intuition as to why the gimbal lock is undesired? Like, I get that it's because like you're kind of losing your degrees of freedom and. But what is the intuition behind why it's like completely well, not completely, but like a little undesired?
So more intuition about why it's not desirable. I mean, maybe this video kind of help like you, if you want to move that ship in all possible ways. Like I think what this GIF is showing is when the outermost and the innermost mechanisms are in that orientation, like you can't rotate that ship item in some orientation. So, but that's mainly the only reason why you can't do that is because if you're forced to rotate that using the gimbal mechanism, then you'll fail. But if you just move your hand, then you move it, you can rotate it whenever. It's only a limitation of the representation. Yeah, I mean, I think it's a pretty strange concept. It is a little bit tricky to fully understand. Like maybe I think this video I found to be pretty helpful. So if you want to look at that. Three blue, one brown also had some video though. Blue before brown, right? Yeah. Yeah. Oh, all right. So are you aware of axis angle? So axis angle is another rotation representation. So again, it still represents some orientation, it's just in a different way. And the way to do that is you think of it as having some unit vector. So here is E, if you take the one from Wikipedia, it's just E. And then there's an angle theta about that axis. But the key is that E is a unit vector, but it can be anywhere and it can be pointing anywhere, basically. And basically there's a theorem that any rotation or sequence of rotation of a rigid body in 3D space is equivalent to one rotation about a single fixed axis, which is basically a similar argument that we made before about why the Euler angles are a valid rotation representation. So it's something similar here. So the good news is it's pretty efficient. So it's another three-dimensional representation. Like you just need three numbers to represent rotation, which is the minimum that we can get away with. And it doesn't have, it does have some singularity, but the singularity is different from the gimbal lock. We're going to talk about that next slide. All right, any questions about the axis angle? Yeah.
Is the axis angle, like, is the unit vector E supposed to be the resultant vector of the three axes, or is it just some arbitrary vector?
Oh, so E is just, oh, so well, So E is just some arbitrary vector that had magnitude 1.
It's got nothing to do with 3 axes.
It does not have anything to do with the 3 axes. So I don't know why they named it E in the Wikipedia, because E is like, it's not the same as the 3 coordinate axes like X, Y, and Z. It's just some arbitrary vector in 3D space. Like it could be, you could have E be like, 42, 31, 20, then you divide everything by the magnitude, you get norm of 1.
So I guess what I'm trying to say is it's not, it can point in any direction, basically. It doesn't matter what direction.
Yeah, you can point anywhere. So it can point, yeah, anywhere in the sphere, which is basically anywhere. Yeah. Yeah. So here's my question. So the unit vector is E, right? So this is the unit vector. So what that means is this vector needs to have magnitude 1. So you take the Euclidean norm and then it's 1. So what happens if you want to represent the identity rotation? I should also, actually, I should also mention that actually most of the time when people talk about axis angle, like the angle theta is actually you can reparameterize it as like your angle theta can instead be set as the magnitude of your vector. Then it's not a unit vector anymore, but you put that axis, you put the theta into the representation of the unit vector. So it's like it's 3 numbers no matter what. Like you can set this to be, so you can set it to be 1, which means it's 3 numbers. So this thing means you set 2 values of E. The third one is like fixed for you. So you only get 2 numbers, and then the third number is your theta. You can also, if you want, you can also change it so that you don't make the magnitude 1, you make the magnitude equal to the angle theta. So those are 2 different ways that you can like implement that axis angle thing. So either way, it's a 3 number representation. Even though there's like 4 quantity, like the 3D and then the 1D angle. Yeah. So hopefully that intuition kind of makes sense. Yeah. Well, I meant 2 independent numbers. So, what I really meant is like 2 independent numbers, and then the third one is determined for you. Yeah, that's what I meant. All right. So, what are some of the problems with the axis angle representation? So, if we want to set there to be no rotation, so your angle is 0, then the argument is, well, you can make your E vector can point anywhere. Right? Does that make sense? Like if you have no rotation, then doesn't matter where your E is pointing. Yeah. And so those kind of things are a problem. Like if you want to represent something, but there's an infinite number of things you could have, then that's an issue for like if you're doing like algebra on things, it's a big problem. And if you are, so if you're setting the angle to be high, which is 180 degrees, then you have your vector is pointing somewhere, it's rotating 180 degrees. Then that seems like it's the same thing as like you can flip your axis the other way, rotate 180 degrees, and then what happens? Like you rotate in the opposite way, but you end up in the same spot. So yeah. Yeah. So and there's also some other issues, like if you're trying to, I guess, interpolate between different rotation, which people often have to do in robotics, for example, then doing some like this type of naive addition, like you have this rotation and then this other rotation, and then you try to take their difference, it a little bit, you have to do a lot of other machinery to get this type of thing working. So like if you have 179 degrees and then negative 179 degrees, they're off by 2 degrees, like not 358. Or you can argue they're 358 degrees, but the real distance, like they're really close rotation. So that kind of thing is missing from those types of representation, the closer you are to the singularity. So. All right, question? Yeah, but what?
Can you explain the angle being 0 again, where you say every axis is the identity of rotation, the first point?
Okay, so maybe we can draw out. Let's draw one. All right, so this is our, like this is one choice of E. Now, the theta is how much you rotate it out. So if we make theta 0, then this thing is just the same. So if I make this E, like maybe E fine, and then theta is 0. Right? It's rotating about by theta, but it's not yet rotating to made it 0. So the whole sphere is the same. Like if this is like the Earth, it will be the same thing. So yeah, it doesn't matter which E you pick. And yeah, that's a problem if you're doing matrix algebra on. All right, any other questions on the axis angle before we move on to the some of the better representation? All right, so quaternion. So quaternion are a 4D rotation representation. So now you have 4 numbers that you need to represent them. So it seems like you added in another number, so there must be a reason for that. So, but just the way that, all right, so the annoying thing is that there's many different ways that people write out quaternions. So you can write them out like this, where you have A, B, C, and D, and then the I, J, and K are like your imaginary part. So remember the imaginary numbers, you square I is equal to like -1, even though you square a real number, it should never be negative. So hopefully that is remembered. So if you're writing it like that, then you would take all the real numbers and in code or whatever you're using, you would just write out the quaternion like A, B, C, and D. So if you're using like Isaac Gym, which is another simulator I covered earlier this class and before, you would just do like W, X, Y, Z, or sometimes it's X, Y, Z, W. So just be careful about the ordering too. So and if you're using like modern robotics, sometimes people use Q. So it's like Q0 plus I Q1 and so on. So my recommendation is, this is the definition, but just worry about the real part. So only worry about the real coefficient and just make sure you know which real number is the real part and not attached to an imaginary number. Like for this Q, the Q0 is like the not attached to any of the imaginary ones. And then you have the other real numbers. So you would write it like this. Yeah. And then you would make the, like, again, if we consider unit quaternion, just make sure that the norm is 1. Yeah. So this is like, the definition or common notation that people use. Yeah. Hopefully you're using some code that makes it clear, like what number you should put in for this. All right. All right, is that clear? Yeah, well,
So all 3 of the imaginary variables, the I, J, and K, all of them equal the square root of -1, right?
so are these all equal to like the square root of -1? If you oh yeah, if you take the square root of that, yeah, basically. Yeah, it's just like if you look at the constraint that they require, like that's like it defined this thing where you have this also hold true. I mean, when all right, I'm writing it like this because this is like the formal definition, but when I code up stuff in robotics, I don't care about the imaginary part. I use code that just exposes, here are the 4 real numbers that I put in. And then your code should handle it for you. So, yeah.
Just curious, why you need all the vectors to be
Oh, so why do we need the quaternion to be unit 1? All right, I think so in general, if you make things unit 1, it simplifies a lot of things. Like you know that you're dealing with the same like distance vector, and if you make things unit 1, I think that it imposes a certain constraint on it. Though it's like this lived in a 4D space, but the constraint essentially removed like 1 dimension, so it lived in a 3D. So this represents everything in a 3D space, which is the space of rotation. So I think that's the way to think about why you use unit quaternion. We can double check that offline, but I think it's to enforce the right constraint that it covers that it only covers the space of 3D rotation. So, and also when you make things unit, it just makes a lot of calculations simpler too. Yeah.
what I'm thinking is that if we force a vector to be a unit vector, sometimes we have to make all the 4 integers into 4 decimals. So actually the calculation in the computer system won't be exactly the same when we're using the integers.
So are you worried about having to change like B to be like from integer to like floating point numbers? I'm not worried about that. Like I wouldn't worry about that. That's not something to worry about. Yeah. These are just some arbitrary floating point number in your computer. Yeah. And if you want to do the math or like have rules on how to multiply and add quaternion, like you can just follow some of the rules here, or better yet, just call it somewhere in your code. I mean, you can write out the algebra for that. I mean, I'm not sure if it's a productive use of lecture time to do that, so you can do that in your own time. But I think the bigger thing is just to understand like what it means, what this conceptually means. So when you're multiplying quaternion, it's like you're composing the rotation. So you do one rotation and then do another one. If you're adding quaternion, would that mean that you're trying to find some like this quaternion plus this one? That means that's more useful for trying to find like intermediate orientation between 2 things. So yeah, so just that's what multiplying and adding quaternion means. If you like if you're looking at code, just double check if you're supposed to add quaternion or multiply them. Yeah. Very, very common bug that appears. And yeah. So if we had to summarize some of the most important properties of quaternion to know, then the quaternion, the nice thing about this representation is that it avoids the singularity that were in the 3D representation. There is a double covering. If you negate the quaternion, you get the same orientation. Yeah. And one reason why people like quaternions a lot is that you can interpolate between them. So by interpolation, what I mean is you have two different orientations, and then you're trying to find like, you want to be able to find something like this for all values of like this thing here. So it's like you're taking, maybe 90% of one rotation and then 10% of another one, or maybe what's the rotation that is halfway between two other rotations. And if these are our rotation matrices, this is not a valid, math equation. But if they're quaternion, you can do something like that. So, and I also found this very interesting fact about a lot of composition. So, like, I wasn't aware of this before, but like if you multiply so many matrices together, you have to end up orthogonalizing them again, which means you make R transpose times R equals the identity. But I guess because the quaternion, maybe they involve like only fewer arithmetic operators. Maybe you don't get those problems. At least this is just what people have found in practice. Like, yeah. And I would recommend if you're using code, my favorite one is PyQuaternion. So that's my recommendation. And any questions about that? I know it's going pretty quickly. Like this, we're not going to be an expert on quaternion, but the more important thing is to understand some of the properties and why people use them. I think that's the more important takeaway. All right, one more rotation representation, then we'll take a break. I know it's it's going a little bit more. So this is another rotation representation by this very awesome paper. So this is a different type of thing that you can use to represent an orientation. So here's the intuition of how this works. All right, you have a set of points in 3D space. And then what 3D flow means is that there's a 3D vector for each point. And if you imagine that this is some 3D object, you have a whole bunch of points on it. The 3D flow will tell you for every point where it's supposed to be. And then you apply the flow to move from here to the next set of points. And then you use like a math technique to reduce everything to one rotation. Because what happens is, like, you have a whole bunch of points, you have flow vectors that cause this point to move here, this point to move here, but this point could move here, so you can't get one rotation out of that. There's like a whole bunch of rotations. So what you really have is like a set of points before, a set of points after. You can find a single rigid body transformation that minimizes the distance between the two. And then that is a single translation, single rotation. That's a really cool part. Yeah. So this is my favorite 3D rotation representation. So, I think it's time to take a break. So I know I've been talking a lot about this thing. So we'll be back in about 4 or 5 minutes. So, yeah. I will. I got accepted. Yeah. So Yuhan, what's your favorite rotation representation? Why not? What's your favorite rotation representation?
The quaternions, because I've used them a lot in Unity. And I think that's where I actually like read about them more. So it was, yeah, it was fun to understand them.
You make the software?
Yeah, for game development.
OpenGL as well.
OpenGL.
OpenGL.
Maybe one more minute. All right, maybe we should get back. So, yeah, I hope everyone had a good break and, had some time to think about your favorite 3D rotation or rotation representation. So continuing on from my favorite rotation representation, you can think of this this is not just a rotation representation, it's also what we mean by a 3D visual representation. So what that means is, what this term means is 3D, because we have a point cloud, which we'll talk about in a few slides. That's a 3D thing. And it's visual because we get it from like camera sensors. So that's what I mean by 3D visual representation. So this is a nice connection between the first half of today and the second half of today. So a quick review of visual perception and representation. So if you're working with some, robotics code, like maybe you'll have information, some information that we call the state information, which is like a set of, maybe it's a set of poses for a different object in your scene that a robot is interacting with. But in the real world, it's very common that, you might only get partial observability, you might not have that access to that direct state information. But what you might have is a set of visual sensors, which is pretty standard. Like you put a camera on a robot, then you get some visual data. And by visual representation, like maybe the most obvious one, the first thing that you might think of is, well, some RGB data, which are images from a camera. And then what a computer sees is like, you have some image and then you get a whole bunch of numbers. And then this thing together is like a visual representation. But it's also in 2D, right? Yeah, so this is 2D, but in robotics, so I mentioned earlier in class, we often want 3D data because we have to perceive like the distance between maybe where a robot's gripper and the object that it has to grasp. Like you need the distance in order to like calculate the right trajectory to grasp something. So this is why I wanted to talk about 3D representation. So some examples of different 3D representation that you might encounter when you're working with robotics are, you might get depth images or like depth data. You might get point cloud, you might get voxels or occupancy grids, you might get triangle and surface meshes, sign distance function. And the fact that we have all of these, once again, it's like in the rotation case, you have different options. And then you might prefer some of them over another. Right? Yeah. Because otherwise they wouldn't exist otherwise. So now one thing that is important is with rotation, you can go from one rotation representation and convert it to another. Like there's formula to do that for basically every possible combination of representation. You can still convert from one 3D representation to another, but you might lose information. So that's the difference between converting from one 3D representation to another versus one rotation to another. Yeah. So do you see why you might lose information? Because like when we'll cover like voxel grid later, and voxel grid are like you make a cube and then you have smaller cubes in it. It indicates like if the object is intersecting with the cube or not, and then you set the number to be like 0, 1 for a cube, or there's different options there. But if you make the cube resolution very coarse, then you lose information. So that's one example. All right. All right, depth information or depth images. So, and for more, you can see my this awesome blog post by this awesome author there. So yeah, and then there's also a an awesome GitHub GIF, like you can try some code to process depth images by me. Yeah, this is my middle name, so it's my first name, middle name, and then last name. So yeah. But anyway, just a little bit of sorry for the self-promotion today. But going back to what the definition means, so the depth images, they're like, you can think of them as normal color images, but the value in each pixel is not RGB, it's a depth value. Like it's the distance in, it's the distance in meters or millimeters, depending on how you set your camera, but it's some distance from the camera to the nearest, point in the world. Right. So each pixel stores a depth value. And when you have depth camera, they will typically have some minimum and maximum range. So they might not see values that are like super close, but then at some point further in the distance, they get less reliable. Then what people often do is they just cut it off at some value. So you get some minimum and maximum, and then you can rescale to 0 to 55 to make it human readable. So if you look at this, this is an example of a color image. This is an example of a depth image where if the pixel is darker, that means the distance is smaller. Right? Does that make sense when you look at the image? And I should say this depth image is much cleaner than you'll ever see in the real world. So if you work with real world depth cameras, you'll see a whole bunch of black blobs that indicate missing data. So just warning you in case you want to use depth images. Like the common complaint that many people have with working with depth images. Yeah. And so you might be asking, well, what are some of the advantages of depth images? Well, the first thing is that you can measure distance. So now you know which part of the image is closer to the robot than the other one, than some of the others. Like that's important if the robot has to like reach around something and consider all that in its planning. But another nice thing is you can make it invariant to things like colors and texture. So if this color image, if the floor or the whatever that object is, if it changes color, then your method should hopefully work the same. If it only uses depth, then changing the color should not change what your algorithm does. So yeah, the way that depth is often computed, so there's a couple of different ways. I cover more in my post. So you can look there for more, but one common way of getting a depth image is you have a camera. The camera source shoots some light ray, some beam of light, and then it hits something, and then you measure how long did it take to go from the camera to the object and then back. You measure that distance, and then you divide it by 2, then you get your the depth value. Yeah, but I think that's what meant by the LiDAR or time of flight thing. Yeah, and if you're into cameras, the Microsoft Azure and Intel RealSense are like the two that are very commonly used in robotics work. Now, another nice thing about depth images that I find pretty nice is that since I learn a lot but I use a lot of machine learning and we use a lot of learning from images. And so we often have some machine learning model like a neural network that takes in some image. That image is going to be a color image, but you can also add the depth value as other channels. So you get an RGBD image. And sometimes, yeah, so I pair it up, so it's RGBD, or sometimes I triplicate the depth so that there's 3 copies of it, and then that makes neural network like kind of treat depth as an equal part of the data, the color image. So, yeah, so this is something I often do. Yeah. All right, any questions or complaints about the depth image? Oh. All right, point cloud. So maybe some of you are familiar with point cloud, but let's just briefly review from the very beginning. So a point cloud is just a set of points in 3D space. So more formally, you can implement them as like an n by k array of n points, where n is some value, like maybe 1,000 or 2,000 or whatever. So the question is, what information do you include for each point? Now, the most basic one is the XYZ position, because the whole point of point cloud is to give you a 3D data. And so you want to set a point, each has XYZ information. So that's why we have this here. But when you're forming point clouds, you get n points, each has a position, but you can also add in more things. You can add in what are the 3 color values. You can add in a 3D like surface normal vector. You can add in more information too. So what, like sometimes if you're working with segmented point clouds, you might also need what is the object that this point is on. And then you might have more information in each point indicating what object it corresponds to. Yeah, and you can get the point cloud from depth information with camera information. So you combine those two, and then you get your point cloud. Just make sure you just call some code from like Open3D or other software that gives you the point cloud. So you might be asking like, what's the advantage of a point cloud? Well, it is a 3D representation like the other. It is robust to color and texture, but yeah, the depth was also like that. But I also think that sim to real transfer has also been easier for people who rely on point cloud representations. And it feels like a much sparser view of the world. Whereas if you have like image information, you have to account for like every possible pixel. But I guess with the point cloud, you can just sort of narrow down on the geometry of interest here. And also point clouds are closest to the raw output of what a camera gives you. So that's also like advertised as another reason why it's good to know how to deal with point cloud. So this is an example from this, not my work, but it's from my postdoc advisor's lab. So it's not really unbiased, but it's still a very good paper. Oh, so what this is showing here is like a refrigerator. And in this paper, they were trying to show you can learn something in simulation using simulated point cloud, learn some kind of manipulation policy there, and then directly apply it in real, using the real world point cloud. And so they were using this example to show like why the sim and real point cloud look visually similar. So, yep. Any questions on that? All right. All right, voxel grid. So a voxel grid is, again, it's another type of 3D representation. So you can think of a voxel as like a cube, and then a grid is just a set of them. So this is like a voxel grid. Each of the cube is a voxel. So it's sort of like the 3D analog to a 2D image. So every single cube here can store like one number, or maybe if you have RGB, it might have to store like three things, and then you get like three cubes or whatever. And then, each of the cubes can have properties. So again, it's also like point clouds in that each cube item can store some varying amount of data. And one way to kind of visualize this is like, I think this is like a common, bunny example that people in computer graphics use. And if you have a point cloud here, you can convert it to a voxel grid. And when you look at something in a voxel grid, you should be able to see like roughly what is the voxel dimension, like what's the resolution there. So yeah, so this is like every single cube is, colored if it intersects with the object or not. Yeah. And then there's something to note about in terms of like the advantages and disadvantages. So if you're doing things, if you really need to explicitly represent what is free space, or if you need to represent the interior of an object, then you might, like the voxel representation might be useful because you have to indicate something for every single cube, where every single voxel had to have some information. It might not have any real world object in there, but then it has to explicitly say that there's nothing in that voxel. So if that's important, then that could be very useful. So like if you imagine with the point cloud, we don't explicitly get the free space. We only have a set of points. And then we kind of have to, if we needed to understand where's free space, we would have to construct that from the point cloud somehow. So the point cloud doesn't give us that directly. And so the counterpart is if you have a lot of free space, then it also feels a little bit inefficient to use voxel grid, especially because of all the storage requirements. And if you're running deep neural networks, if you read papers that say, we're going to learn from voxel with deep neural network, they all say, well, it's going to take up a lot of memory. So make sure you have a big GPU or whatever. Yeah. And there is the thing that I mentioned about potentially losing some information if you go from point cloud to voxel, or also from voxel to point cloud. Like you can lose information going from one to the other. All right. So anything we should talk about? Yeah. Well,
Just curious, were we trying to store the voxel grids? So as you said, it stores the data as a bunch of voxels. So it just actually stored the vertex, the each vertex around the cube, or some other properties of that geometry.
so are you asking like how do we actually store it in like a computer or whatever? I mean, I think there are different ways you can do that. Like I think the easiest way to think about it, if you've used NumPy before, you can write numpy.array 100, 100, 100. And then you get a 100 by 100 by 100 voxel grid. And then each of those items can be one number. It's like you have maybe so you have like np.0, and then you get 100. So you set this to be a voxel grid, and then this is how you can start the storage. In NumPy, you just make a 100 by 100 by 100 array, or however your dimension you need it. And then you start like assigning stuff to it, like the grid. you start assigning things to it. Like this is an example of how you can do it. One nice thing about voxel representation is that this kind of thing is very easy for ChatGPT to generate. So you can actually generate voxel representation pretty nicely because it's more structured in some sense. So, yeah. All right, here's another representation, triangle meshes. Yeah, so we're in like computer graphics today, basically. But you do this, when you study this, you'll often see computer graphics notes, but this is still very important in robotics because we need to know 3D data. So for triangle meshes, this thing is a surface mesh. So it's not going to represent your interior, which is something you might be worried about if you need to represent like interiors. And in data, when you put it in data, you store it as a set of vertices and triangles. So you have a bunch of triangles, store their vertices, and then in some data structure, and then the whole combination of them, you can render them by using you can also render them by using the like marching cubes algorithm. If you've seen how this works, like this is one way you can actually generate the full surface from some function, basically. So these are some example visualization of different resolution of the triangle mesh. And so one of the nice things is that with the point cloud, you're kind of restricted to like the quality of how many points you can get from your depth camera, which is gonna have some imprecision. If you're designing a voxel grid, if you're designing a surface mesh, using maybe some implicit function with marching cube, you can make the surface at a really fine-grained resolution. So this is also one reason why triangle meshes are often used in graphics, and other application where you need a really precise surface of something. And yeah, this figure here is just from one of the like blog posts about how the marching cube algorithm works to actually generate like a 3D data. Like there are different ways that you can, all the different possibilities of whether if you have some cube in it, then which parts of it intersect with which part of the function. So yeah. But again, we won't go through that in detail. I just wanted to make sure that you're aware that a triangle mesh is one example of a 3D representation. But it is also it is a representation that I feel like it's not as popular in robot manipulation as compared to like depth or point cloud. Yeah. All right. I think the last major 3D representation will be based on sign distance function. So you can think of them as you have some function. It represents some 3D thing. And then you have some arbitrary point in 3D space. The function will give you like some number. If it's positive, then it's supposed to be outside the surface. If it's negative, it's like inside. And if it's 0, it's the surface. So it's a little bit easier to think about in 2D. So in 2D, you have some function f of xy. For all the points xy equals 0, you form a curve in 2D. So just think of that, but in 3D, you get the 3D representation of some surface. So it's implicit because you don't like just get the surface. You actually have to like, you're really just given some function, and then you have to try out all the values of x and y and z to actually form that surface. And the really nice thing is, depending on the nice thing about the sign distance function is this thing probably gives you the most amount of resolution. Like you can basically get infinite resolution by trying out all possible x, y, z values. So this thing is like the most amount of resolution that you can get in a 3D representation. And the visual of like what it means when you talk about like distance and gradient information, like you can basically get, like I took this figure from like one of the sources here, where if you're looking at the surface and you're trying to find the greatest rate of change from any point on it to the rest of the space, then you can just call the gradient, and then you just get that. You take the gradient, you evaluate it at different x, y, z, and then you get the information there. Yeah. And then I wrote some potential drawbacks of this representation. So I mean, if you're okay with an implicit representation, then this is probably pretty good. And I think today sign distance functions are very popular in like computer vision research today, if you're familiar with some of the stuff that's going on now. So any questions on that before we just close discuss some concluding thoughts? What's your favorite 3D visual representation? Nobody has a favorite. All right, well, let's move on. So, all right. So just some other consideration if you're working with 3D representation, especially in robotics. So if you're doing like robotics plus machine learning, which is very popular today, it's the kind of stuff that I think about a lot, then if you're trying to learn from 3D data, depending on what the data is, you might need a specific neural network to do that. So for example, for point clouds, there's specialized neural network called PointNet and PointNet++ for learning from point clouds. So, like convolutional neural networks are specialized to like 2D images. These are like the analog, but for point cloud. And, the reason is they have to take into account the fact that in a point cloud, you can change the ordering of the point in the data structure that you're storing it. And it should mean the same thing. You should get the exact same output. So that's why we need some specialized, architectures for that. And one thing that you will probably have to do in practice is, because occlusion are a major problem, like you read the paper, then the limitation section, if it has one at all, like should say something like the method is not robust to occlusion. Yeah. So one solution is put multiple depth or color or depth cameras like at different locations, and then you fuse them together. So you can do that with like fusing point cloud, fusing other representation too. Yeah. But I guess one of the last things that I want to say is like one of the reasons why I think it's important to talk about 3D visual representations is that if you are going to try to do a robot manipulation task, sometimes it's much easier to learn something from a specific representation than another one. So a good choice is going to make your manipulation a lot easier. And that's a very prominent like research theme. So I'll just give one example. So just the one on the left-hand side. It's from the same like point cloud example, the point cloud slide that I showed. But the summary of that these authors were trying to determine for any articulated object which exists anywhere, like you have like laptop, you have like other covering, then what they wanted to do was learn a good 3D visual representation that showed if you were to open up the object, where do all the points in the point cloud move? And if you know that, then it's very easy to design a good manipulation procedure by picking which point has the longest vector, and then you just pull in the direction of that vector. So we're not going to go through the details here, but the main takeaway is good choice of 3D representation make your manipulation a lot easier. So that's why it's important to study these topics. So to summarize, we covered some rotation representation, we covered some 3D representation. And next week is the last week before the last week of lecture. So we will cover some special topics and then final exam review. Yep, I'll see you next week then.